Hi, my name is Antar, and today I will present the quantum Fourier transform and its implementation in Qiskit. What is a classical Fourier transform? Classical Fourier transform is a mathematical operation that changes a given input from a basis or domain to another. You can think of it like a vegetable soup. The soup is the input signal, and the Fourier transform is your senses separating and identifying each individual vegetable. Why do we need Fourier transform? In simple terms, it lets us to examine a signal from a different perspective, often revealing properties that are hard to see in the time domain. Mathematically, it can also simplify certain derivation and solution, especially in signal processing and differential equations. In Figure 3, a square pulse signal is shown in the time domain, where it is not obvious what frequency components are present. By applying the Fourier transform and viewing the same signal in frequency domain, we can clearly see and analyze the frequency content of the square pulse. Classical Fourier transform appears in many everyday technologies, even we are not aware of it. Common examples include active noise cancelling, telecommunication, and medical imaging, such as MRI. Most modern headphones offer active noise cancelling. The headphones captures the background noise, analyzes it in the frequency domain, generates an inverted or anti-noise signal, and mix with the original noise so that the sound waves cancel each other. In communication, Fourier-based methods help separate overlapping signals that share the same physical medium by isolating them in different frequency bands. In medical imaging, MRI scanners measures radio frequency signals from the body and then use Fourier transform to reconstruct spatial images from the frequency domain data. Now that we know about the classical Fourier transform, what is a quantum Fourier transform and what is special about it? QFT, in short, takes states in the computational basis and transforms them into Fourier bases, creating superposition with specific phase rotations. One limitation of QFT is that quantum measurements index is destructive, so the full set of Fourier coefficients cannot be read out at once, each run revealing only one outcome, whereas the classical transform can output all frequency components directly. The main advantage is that its time complexity is smaller than that of the classical implementation, enabling much faster processing of the same input size suitable quantum algorithms. Figure 4 shows the application of QFT to size 0 and how the state changes at each steps as additional phase rotation are applied. What are the quantum Fourier transform applications? First one is quantum phase estimation, or QPE. Uses the inverse quantum Fourier transform to measure the kickback phase from a quantum gate and translate into a binary representation. This algorithm is crucial because it allows quantum computers to calculate eigenvalues of Hamiltonian operators. Another one is Shor's algorithm. Can factor large integers exponentially faster than classical computers. It uses the QFT to find the period or frequency of a modular exponential function. Current secure encryption systems like RSA relies on the difficulty of factoring large numbers. This algorithm theoretically breaks standard of RSA keys. Another application is quantum chemistry and simulation. QFT is used to estimate the phase of a unitary operator generated by the molecular Hamiltonian. This allows for the determination of the system's eigenvalues, specifically finding the ground state energy of a molecule. The HHL algorithm utilizes phase estimation to extract the eigenvalues of a matrix A to solve a system of linear equation defined as AXB. By inverting these eigenvalues in a quantum register, the algorithm prepares a state proportional to the solution vector x. This is the logarithmic problem. Quantum algorithms can solve the discrete logarithm problem by finding the hidden period with an algebraic structure, which Shor's algorithm utilizes QFT to determine this period efficiently, which allows for the computation of the discrete logarithm. Let's break down QFT implementation for different qubit sizes. QFT uses Hadamard gates, control phase rotation, and swap gates. The only exception is 1 qubit implementation. 1 qubit implementation uses only one Hadamard gate, where computation basis states 0 and 1 transforms into equal superposition plus and minus. The rotation angle is determined by the distance between qubits. If the control qubit is k, position away, the phase shift is pi divided by 2 to the k. For instance, half pi rotation is applied to Q1 in qubit 2 QFT. This pattern continues as the qubit size increases. Swap gates are applied at the end of the circuit to reverse the qubit order bit reversal so the output matches the correct binary representation. Now let's talk about QFT implementation in Qiskit. The first example is the implementation of single computational basis state in a 4-qubit QFT. Figure 5 shows the circuit for the input state 0, 1, 1, 0, and the figure 6 shows the measurement results, confirming that the prepared input is a signal computational basis state. After applying the QFT, we expect to obtain a uniform superposition overall basis state with equal magnitude for all amplitudes. What's the result? A 4-qubit QFT is added to input state circuit. Figure 8 shows the result of the measurement with 1,204 trails for 16 states. It is expected to add 64 counts for each state, however, due to the noise, there is a fluctuation in the result. Second implementation is 2 computational basis state with 4-qubit QFT. A superposition state 0, 0, 0 plus 1, 0, 0, 0 used to test the QFT. Figure 9 shows the state implementation and the figure 10 shows a verification of the state by measuring it. We expect to observe constructive and deconstructive interference after applying QFT. Consequently, the measurements results are not longer uniform. Some output counts to near to 0 destructive interference, while others rise to approximately 128 constructive interference. Similar to one computational basis state implementation with 4-qubit, the 4-qubit QFT is added to input circuit. Figure 12 shows the result of the measurement with 1,024 trials for 16 states. The output counts are evenly distributed. Some of the basis states are close to 0, while others close to 128. This variation is due to constructive and destructive interference between the two input states. The specific patterns for this input is even numbers are picked, odd numbers are 0. Noise in the system creates statistical fluctuation in the result. Beyond the Qiskit exercises, I implemented 8-qubit version of it with different states. For single computational basis state, the input state selected as 1, 1, 1, 1, 1, 1, 1, 1. Figures 17 and 18 shows the Qiskit circuit implementation. It's expected that each state will be equal count after the measurement. The result is a uniform distributed superposition state. 16,384 trials were made for 128 unique states for this experiment. Expected 128 for each, which is close, but due to the noise, the data fluctuates. For 2 computational basis state, the input state selected as 00, 00, 00, 00, 00 plus 10, 00, 00, 00. Figures 20 and 21 shows the Qiskit circuit implementation. It is expected that each state will be interference in each other's states. Constructive and deconstructive interferences will be observed. Interference is seen in the result. This experiment has 16,384 trials for 128 unique states. Expectation was 256 for constructive interference, 0 for the destructive interference. Again, due to the noise, the data fluctuates. In conclusion, QFT has an time advantage in comparison to a classical implementation. Applying QFT to a single basis state will always result in a uniform distribution. QFT is one of the backbone modules for a lot of algorithms. My plan is in the future to implement quantum binary adder and the QFT binary adder and compare their performances with different qubits. Learning more about inverse QFT and experimenting with more complex algorithms like QPE or Shor's algorithm. Thank you.